ACE 111, Lecture 14, Set 5. We're going to continue talking about blockchains, Bitcoin hashing in the final project. One thing to remember is that this is actually building on the SHA-256 project that we have worked on earlier. So it would be really helpful when we were talking about the optimization and the final project. You have a presence of mind about what we discussed in SHA-256 and its round. Remember, we discussed all the critical path, like how you would take the WTs and you make sure that the critical path is balanced, and you pre-compute things. The same is true for the final project, but the final project has a set of also inputs and outputs that make it even more complicated. So these are basically, kind of some of the messages that we're going to talk about. Let's think about the WN array. We have the kind of what happens is that we are going to have this if you write it as a function where you have a WN array which has this a big size, then what happens when you synthesize is that it's going to make copies of these registers, like 64 registers, because as you see here, we're talking about the WT new, which is basically computed based on the what is available in the registers. And what WT new does is that it will go through the contents of this registers, and then it's going to do those operations that we had. And this is like an example of those operations. Now, pay attention to this. Basically, we have the right rotation of the WT minus 15, and then we have the right rotation, or the right rotation of this minus 18 and minus 15 and 18 times, or minus 15 kind of the right rotation, and so on and so forth. So what happens is that as you see here, not every time what we are doing is we are computing on all these WTs. In fact, there is a limited set of WTs every time we are doing the computation on. So, if you just go and bluntly define this W in an array, we're going to have a huge array that we have to work on, and that may not be beneficial in terms of optimizing. We're going to use a lot of resources that are not being used in each cycle. Now the question is, how could we optimize it? And this is something we discussed in the context of the SHA itself. I'm just going to go briefly on it, and you see what happens. So instead of trying to define it such that we have this 64-to-1 multiplexer that selects out of this 64 selection, and then kind of does these functions, what we do is we try to have a t where t's maximum is 16, and the t minus 15 would kind of rotate back to the W1. And now what happens is that here, what we are doing is, we are, as you see, we don't have to have all the inputs multiplexed to go to these right rotations and, the shifts. What we do is basically what we are doing is we are just using selectively these inputs, like the W1 here, and then which goes through these right rotation, as you see here, and then it is going to get shifted, and then the OR function is going to OR them, and then this creates the S0, and S1 is kind of similar. It's going to use this W indexed here. So instead of trying to do things like we did before, what we are going to do is we are going to just make sure that the WTs every time the right index gets the right value, and then we are going to compute S0 and S1, and then do the AND function here, basically the add function here. And at the end of the day, this is the new WT for us. Now, if you think about this computation, what happens here is that we have the, and again, we have done this in the context of the SHA 256 alone. We are just going to go through this practice again. Remember, the input to the function is 8 bits. So we have this, this 8 bits, sorry, not 8 bits, sorry, 8 words, A, B, C, D, E, F, G, H. And then, the output is going to kind of get transformation of this is going to be combined with the WT, which is kind of pre-computed, the parts we can pre-compute. And then we are going to put this pre-computed values in here and try to get to the next cycle that is basically a computation of this function. Now, one thing to remember is the critical path. And the critical path, if you remember, is the longest path that is the computation is done before we kind of finalize the computation in each round. And if you see here, the critical path is, when we have this kind of WT come here, and then, it gets to, if I go to the computing here, you will see that. So remember, we have this the rotations, and then we have the, these intermediate variables. And what you see here is that when we compute this value T1, as you have in the description of the function, the values here are somehow, these values have to be computed, the H, the S1, and CH, but the K and W are not dependent on A, B, C, D, E, F, G, H. Basically, these values, we can compute them one cycle ahead. And then, if we compute this W, which will be like, the pipeline in 2 cycles ahead, we can pre-compute things. And, this is something that we could use as a hint. So let me just go back here and think about all the computation that has to be done. Here, what we see here is that the content of the register E, register F, and register H is going to define the CH. The content of the, this E is going to go to S1, and, this also is going to get input from, the KT and WT are going to get, they combined with some operation, and then, get through this P, and then they're going to be combined with what? With the register H, and that is going to create this kind of CH. So if you think about the critical path has to be through this route, right? From this computation, coming down here, coming here, all the way here. And that's like the longest path we could have. Now, if we could pre-compute some parts of this, then we remove this from the critical path, meaning that, at cycle, if at cycle, say, 3, we have pre-computed in cycle 1 these values, and then, we did this, kind of the 2 cycle ahead computation and combined this in the last cycle with this, and then we did this, then this gets out of the critical path. Then the critical path only becomes the path that we are taking from here to here, all the way to the next registers. And that is going to help us have, much better timing of the critical path. So now, that means we have to do some pipelining, and we have discussed pipelining. Just as a reminder, the way we do pipelining is by pre-doing something and have enough resources that while some of the elements are busy, we are doing, if we have the resources, we do something in parallel. Let me just go back to the example I have made in the pipelining lecture, and that was, the example with the pizza oven. So we have a oven, and we have a person which makes the dough for the pizza. And imagine that, making the dough for the pizza takes 5 minutes, and it takes 15 minutes for the oven to bake the one pizza. Now, if I have, if I'm making one pizza, then of course I have to do it 20 minutes. Like I have 5 minutes of the time, which I'm making the dough and like put ingredients on it, and then 15 minutes it's going to be in the oven. Now imagine that, this is kind of pretty good waste of resources, because I'm actually, the person who's making the dough is not, has to be idle while the pizza is getting baked in the oven. Like, they're going to waste for like 10 minutes while the pizza is baking. Now, what if I can pipeline this, meaning that, while the pizza is baking, I also make the next dough, right? So if I'm making more than one pizza, say I'm making like 100 pizzas, what happens is that every time, I don't have to wait 20 minutes for each pizza, because now, like the first time I make the dough, I put it in the oven, that the same time that the oven is working, I'm going to make the second dough, and then, I'm going to do again. And this is just like, I'm basically just pipelining it. So if I'm making more than one pizza and I have inputs coming to my functions, what happens is that I could pipeline it to make it faster. Instead of 20 minutes, I'm doing it in 15 minutes. Now imagine that I actually, instead of one oven, I have two ovens. So I have some parallelism in the system. Now, if I have that, then I could even do better. Like I could, while, I'm making the first dough and making the second dough, I'm going to put it, in the first and second oven, and then I'm going to keep making those and putting it like, in these two ovens. Of course, you have to also think about the optimal capacity of the, of the people who are making the dough compared to the capacity of the oven. There's a limited amount of parallelism like I could do. Like, I cannot do more than 7.5 pizzas per minute if I have two ovens, because no matter how much I pipeline in the beginning, I'm limited by the number of, I'm limited by how much each oven can bake a pizza for me. But that's not the point I'm trying to make home. What I'm trying to make home is that we could set up a pipeline for pre-computing these values, and then that pipeline could help us do these things more efficiently. Well, first of all, this is some, some example for how you set up such a pipeline. And this pipeline will help us, take this WT pre-computed in the previous cycle, and then you use this, assign this to the next value of the W, and then every time we are doing this, we go through the optimization of the SHA function and try to optimize this. So the critical path should go through the SHA-256 op, which we have designed last time. So the critical path computing part can be reduced by pre-computing H plus K. Also the other thing we could do is pre-computing H plus K plus W, which is a little harder. So the W has to be computed 2 cycles earlier, and need to make sure that we have the values in the memory two cycles earlier to do this pre-computation. But the good thing is, because this is FPGA, we could have parallelism. We could use multiple registers to store and pre-compute these values and do the pipeline. So this is something we need to do to optimize the project. Again, as you see here, you know, one thing we could do is we could just compute this, pre-compute this, and then, you know, just kind of come to this P and then do the critical path like this. Or we pre-compute this one cycle earlier, and then, you know, we kind of compute this, and then, you know, we kind of limit this critical path even to a shorter value because we're doing this pipelining. Now, you know, again, going through this computation in a piece of code, that means that, you know, the in a SHA-256 operation, we have the input, which is 32 bits, registers, which is basically one word, and then, you know, we have the eight 32 words registers, and then we have this S1, S0, CH, majority, T1 and T2, which are basically internal signals that we saw on that chart. And now if we do compute these values just as the procedure is for the SHA-256, we see that, you know, we for S1, we basically just take the value of the in the register E, and you know, we do right rotation, and we do the shift, and then we have this, which is basically a CH, which is basically a logic function based on the values in registers E and F and E and G. And then T1 is a combination of this S1 plus CH plus the value in the register H, which is given, plus K plus W. And as you see here, these values were kind of the input logic, but if we could get the inputs earlier, like if we could get the dough earlier and make the pizzas earlier, we could kind of speed up things, right? So now, again, S0 is a function of the A values in the A registers, which is, you know, something that is kind of, we could compute on the fly. And then the majority is the you know, A and B and A and C and B and C, like the content of these input registers. So this can also be done kind of in the logic in parallel. But again, you know, this T2 has to be done after we have S0 plus this majority to compute that. So this one, you know, if you want to talk about the critical path on T2, it has to be, you know, this has to be computed, and this has to be computed, and this is basically taking 2 computation per cycle. But the 256 optimization is T2 plus T1, and T1, as you see here, it has to wait for S1 and CH to come together, plus, you know, the value of H, which, you know, could take another cycle, plus these values. And then, you know, basically this one becomes, you know, the critical path here is really this, you know, computation of this value, or, you know, in senses, you know, T1 is kind of the bottleneck. So this is also kind of a long computation. But if we could optimize this in pipeline to get the K and W, which are not dependent on A, B, C, D, E, F, G, H, so they're not dependent on the other inputs, what we could do is we could compute them one cycle ahead, but then we have to compute W 2 cycles ahead. And then, you know, if we could do that, then we could even do better and have this pipeline, like 2 cycle ahead pipeline thing that can help us get things much more efficiently in terms of the time. So the project challenge is really trying to figure out how to implement this concept of a pipeline in System Verilog yourself. But if you think about this and you think about this hint, that should be pretty straightforward how you could do that implementation. We could even go more aggressively. We could, you know, instead of just K and W, we try to pre-compute, you know, H, but you know, H is kind of equal to G, but this is not dependent on itself. So we could do, you know, H1 cycle ahead. And again, these are all things that you need to kind of write down the code and try to implement in baby steps to make sure that you're not making a mistake. And then you include it in the code. These are kind of what makes a good project, and I expect that you kind of can go through these optimizations yourself. Now, the other thing is, you know, in order to do this computation, we need some sort of a control signal. And, you know, the controller, if you remember, it has a sequential design. It's always the underscore FF and at positive edge of the clock. And, you know, how we write it is that, you know, we try to make sure that we understand the different cycles for a SHA-256 operation. And how we do it is first we read the values in the words H0 to H7, so 8 words we are reading. And then, you know, depending on the state that we are programming, we are preparing the input, or we are computing this value, or, you know, we are kind of having different kind of the values here that are cycled back to the SHA-256 operation from the previous cycle to do the computation of these new values, which go to this 8 registers here. Now, you know, this basically translates to this controller that is written here. The states are, you know, either we are preparing, which means that we are going to put in the registers A to H, which are 8 registers, the input values. And then we are going to compute. If you're in the compute state, we are going to call the SHA-256 operation. And this has several input outputs, as we have seen before. And this is going to generate, again, an 8-bit output, which we are going to put in this A to B registers. Okay, so you know, this is it with the optimizations that we have in the set 6. We are going to continue with you know, the lecture 15 and see, you know, more concepts that can help us get to the best design we can. Thank you.